When we look up into the night sky, we can see stars and galaxies in abundance, their luminescence letting their presence be known. But what about exoplanets? No matter how hard we zoom into the sky, we can't find any. So how do we know that they exist or know where they are? Well, one way you can find out is using the transit method. Transit, in this case, refers to the passage of a planet between us and a star. An example would be with Venus, as can be seen in this image over here, where it passes between us and the Sun. As for how the transit method helps us find exoplanets, it has to do with the brightness of the star it orbits, or in more scientific terms, the intensity of the light transmitted to Earth by the star. To clarify, intensity is a measure of power per area, and in the current context, it is the rate of transmission of energy per area of light. However, thinking of things in terms of per area can be quite difficult, and so we can simplify things a bit by looking at a model where instead the observer can be thought of as a point. In this case, the brightness can be attributed to the amount of light that is transmitted to that point. And along with this model, an approximation we make is that the star releases light in a uniform distribution. That is to say, that whether we look at the top or the bottom, or anywhere on the star, we would be getting the same amount of light. But when an exoplanet passes between us and the star, some of the light is blocked and the intensity we measure decreases. And it's this decrease in intensity that allows us to discover exoplanets. And so, to give an example, here we can see a star, and here we can see a planet. And when I hold the planet in front of the star, you can see that the intensity decreases from 26 lux to about 23 lux. But of course, an exoplanet doesn't just stay still, it orbits its star. And so, as I slowly move the planet around the star, you can see momentary dips in the intensity where it again goes from around 26 lux to around 23 lux. This repeats again and again, and once you can confirm that the dips are regular and consistent, huzzah! You've found a star. And of course, the transit method doesn't just tell us that the exoplanet exists, it can also tell us other things about the planet, such as what the radius of the planet is. To see how that works, let's take a step away from this for a second and look at a model very similar to the one from before. The stars in the sky are extremely far away, so much so that the distance between the planet and the star are comparatively negligible, and we can approximate them to be roughly the same distance away. And this approximation manifests itself in this model by the fact that the rays that are transmitted to the observer are still relatively parallel when they are blocked by the planet. And since the light that is being emitted is still relatively parallel, we can consider the distribution of light in the following way. The light that is transmitted to us, the observer, has a uniform circular distribution, and as such, the total light transmitted to us is proportional to the area of the circle squared. And therefore, it is proportional to the square of the radius of the source, which in this case is the star. If a planet were to then come between us and the star, some of the light that should have been transmitted is blocked. Then, in a similar fashion as before, the amount of light that is blocked is proportional to the square of the radius of the planet. If we were to look at the data from the full star and the full planet from before, the intensity when the star isn't being blocked, which is around 25 to 26 lux, is proportional to the radius of the star squared. The lower intensity, which is around 22 to 23 lux, is the intensity when the planet is blocking the star. The difference between the upper and lower intensity corresponds to how much light is being blocked, and it is this number that is proportional to the radius of the planet squared. With these proportionalities in hand, we can see that the ratio of the numbers on the left side and the ratios of the numbers on the right side are equal, where the ratio on the right side has the pi's cancel out. Such, if we have measurements of intensity and we know the radius of the star, we can use these to calculate the radius of the planet. And so, with the transit method, we're able to find an incredible number of exoplanets just by looking at the minuscule changes of intensity of the stars in the sky.